So in this lecture, we will use all the rules and whatever we have learned so far to take an example and see if we can write a character table from scratch. Okay, so let us take an example XEF4 and see what all we know so far, whatever we have learned in this course, and can we write a character table for this particular molecule. So I'm not telling you as of now what is the point group, what are the symmetry elements or symmetry operations present. So let us do it from scratch. Okay, so the structure of the molecule is square planar. So if I try to write down, so it looks like this. Now we have learned how to orient this molecule along the axis, right? So let us, because for unit vector transformations, it will be important to orient the molecules along the axis. So you have X, Y, Z, and you have X, E along the center with, let me use different color, 2 XEF bonds along X-axis and 2 XEF bond along Y-axis, right? That is Y and minus Y, XEF, right? So now we should be able to comfortably tell where all the symmetry elements are present, right? So let's see. So now let us try to list down all the symmetry elements and then corresponding operations. So we'll first write down the elements here. So this particular example will revise everything what we have learned, and we'll be able to write down the character table. So I'm taking this example because this is highly symmetric. So we can also take octahedral example, which will be more symmetric than this, but then that will take a lot of time in calculation. So I have picked up a reasonable example where the order of the group is high so that we know a lot of elements here. Okay, so let's start with E. Then you have C4 axis, which is lying along Z, right? Collinear C2 axis, which is also along Z. Then you have, let's call it as C2 prime, which will be lying along FXEF, which is along X-axis. So this is basically a C2 prime, which is lying along X-axis. Then you have C2 double prime, let's call it as, which is lying along X and Y-axis. Now what else do we have in this? We have inversion, right? Inversion center is there. So you have FXEF, everything is getting inverted here. If I will be lying along XE, right? Then what else do we have? We will have S4. So S4 will be collinear with C4, and we have a sigma H over here. We also have S2, but S2 is basically I, so we don't write S2 here. And there is no S3 or C3 because this is containing 4 atoms of fluorine which are separated by 90 degrees each. So there is no C3 in this. Okay, then what else we have? Sigma H is the molecular plane which is lying along the XY plane. Then we have sigma V, which will be lying along, there will be 2 sigma V's, right, which will be lying along XZ plane and YZ plane, right? Then we have 2 sigma D's, which will be bisecting the XY axis and containing the Z axis, right? So it will be something like this, right? And similarly, we have another sigma D, which will be bisecting X and minus Y, right? So something like this, right? Okay, so now that we have listed all the symmetry elements, so I'm not calling it as group elements. Now let's look at the symmetry operations present in this. So E will give you one operation, C4 will give you two operations, C4 and C4 cube, because C4 square will be C2. C2 will generate only one operation because C2 power 2 will be E. So this C2 prime, there are actually two C2 primes and two C2 double primes, right? This two C2 primes will be one along x-axis, one along y-axis, and the C2 double primes will be in between xy axis and in between xy axis, like this, right? So along the sigma d's, basically this will be along the sigma d's. Okay, so this will be generating the similar number of operations, C2 prime to C2 double prime. I generates only one operation. S4 will generate how many operations now? So S4 will generate two operations, right? Sigma will generate one. Each sigma v will generate one. So there are two sigma v's, so two sigma v operations and two sigma d operations. So this tells me that the order of the group H, let us count all the symmetry operations. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So H is 16 here. Okay. And I'm not going to do all the class calculations, but we will just see here number of classes. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 classes. So we have order of the group, we have number of classes. Now let us also see what will be the point group here. So point group will be, because there is one C4 axis which is principal axis, and we have four C2 axis. So there is a Cn axis and n C2s perpendicular to Cn, right? So we have C4 and four C2s perpendicular to C4. This will be falling into D4 point group, and because there is a sigma h present, that takes us to D4H, right? So point group S calculation is very simple. So D4H point group. Okay, so now that we have determined what are the symmetry operations present, order of the group, number of classes, D4H point group, let us see if we can write down the character table using this information. Let's go to writing character table. So we have listed all of them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Okay, so since there are 10 classes, so there has to be 10 irreducible representations, right? So we have tau 3, tau 4, tau 5, tau 6, tau 7, tau 8, tau 9, tau 10. Okay, now the first rule, which says that the summation Li square is equal to H, right? So that tells you that L1 square plus L2 square plus L10 square should be equal to 16, right? Okay, so because these are dimensions, so character under E will take the value as L1. So this cannot be negative or fraction. It has to be a real number, or it has to be a natural number. So 0 is also not an option. So starting from 1 and above. Okay, so now if we take all 1, let's say, So we will get 1 square plus 1 square. So that gives me 10, right? So that does not give me 16. So that means at least one of this will have two-dimensional representation. So if I take 2 here, that gives me 9 plus 4, which will be 13, right? So if I do this, then I get 13. So if I add one more 2, then I have 8 plus 8, which gives me 16. So I can say that there are 8 one-dimensional representations and 2 two-dimensional representations, right? So very clearly I can write 1 characters for character under E, right? So this is 2 and 2, right? Okay. Now also I know that summation over all r I r square is also equal to h, right, which is 16. So that means for any given representation, if I take the sum of squares under characters of different symmetry operations, I should get 16, right? Okay. And this would also be multiplied with the class sizes. So this would mean that if I say this, that okay, let's say this is A, B, C, D, E, F, G, H, I. Okay, let's go to second page, next page. So this gives me 1 square plus 2 into A square plus B square. Let me just write down the corresponding symmetry operation so that we know what are the class sizes here. C2, 2C2 prime, 2C2 double prime, I, 2S4, sigma H, 2 sigma V, 2 sigma T, plus 2C square, plus 2D square, plus E square, plus 2F square, plus G square, plus 2H square, plus 2I square, right? This should be equal to 16. Okay. So now if you see that if I put all of them as 1, so do I get the value 16? Let us see that. So this gives me 1 plus 2 plus 1 plus 2 plus 2 plus 1 plus 2 plus 1 plus 2 plus 2. So I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I do get 16. So that means one of the solution is all of them can be 1, right? So I will just erase this and I will substitute it with 1. All ones is one of the solution. Now let us go to next solution. So the values here can be positive or negative 1, right? Because negative 1 would also give me 16. Now what all negatives it can take? It can take half of them should be negative, half of them should be positive. Why I say that? Because I can say that tau 1, tau 2 would go to 0 if half of the products will be positive, half of the products will be negative. And then we also have to factor in the class sizes here. Okay. So for example, if I'm making A as negative, so that would mean my this 2 is becoming, so I have to have 2 other values as negative, right? So if I, for example, if I have A as -1, then I have to have at least two positives to counter the negative of A as positive values. So for example, then B and E has to be positive so that the overall tau1 dot tau2 equal to 0. So if let's take the tau1 dot tau2 equal to 0 condition and see how does it, what do I mean? Okay, now again let's see, tau1 dot tau2 condition is 1 dot 1 plus 1 dot 2 dot A plus 1 dot 1 dot B plus 1 dot 2 dot C plus 1 dot 2 dot D plus 1 dot 1 dot E plus 1 dot 2 dot F 1 dot 1 dot G plus 1 dot 2 dot H plus 1 dot 2 dot I should be equal to 0, right? So this means if I'm taking A as negative, so I have created -2 here, and then I have to take two positives to cancel this, right? And similarly, I have to cancel all of them together so that half of them are positive and half of them are negative, right? So that would mean that, okay, let us take A as negative. If I take A as negative, then my B, so because it is 16, the overall sum is 16, so I should have at least 8 negatives, 8 positives, right? So let's see that, how does it come? So 1 minus 2 plus 1 minus 2 minus 2 plus 1 minus 2 plus 1 plus 2 plus 2. So if I do this, you see that I have deliberately chosen A, C, D and F as negatives. So that gives me 2, 2, 2, 2 negatives, and then 1, 1, 1, 1 plus 2 plus 2. So 8 positives and 8 negatives, giving rise to 0, overall 0. So we have to consider all such solutions where total of 4 terms are positive and 4 terms are negative, or total of +8 is coming and -8 is coming. And if I keep doing that, I can find all the solutions, right? Because this is the orthogonality condition which will follow. So let us write down the solution. So I'm just now going to write down all the solutions. I'll just read out from my notes. Okay, so we have 1, 1, -1, -1. So I take 2 2's as negative. Then you have 1, 1, 1 over here, and -1, -1, right? So this gives me tau1 dot tau2 equal to 0. This satisfies that condition, and also it satisfied the summation over all r. The sum of squares will give you 16, right? So both the conditions it has to satisfy, it does satisfy that. Also, each of this should follow the orthogonality condition. So if tau2 is orthogonal to tau1, it should also follow that tau2 dot tau3 is also equal to 0, tau2 dot tau4 is also equal to 0, and so on. So that means as we keep on solving, we increase our chances of solving to a perfect number. So that means less of hit and trial as we move forward, right? So for example, now for tau3, we will have 3 conditions. One condition comes from here, and 2 more conditions will come, tau1 dot tau3 equal to 0, tau2 dot tau3 equal to 0, right? So both these conditions, you can form the equation. The equation is now simple, as we have seen, and I'll just read out the answers directly. So you have -1. The concept is same. So I'm not going to do all the calculation, otherwise it will take forever to just show the calculations, which is now trivial because we have already seen that. -1, then you have 1 and 1 and -1. Okay. So again, what I have done here is I have taken negatives in front of those symmetry operations where the class sizes are 2, right? So here 2, here 2, here 2, and here 2, right? But I also have to take care that, so using this, tau1 dot tau3 will be equal to 0, but I also have to see if tau2 dot tau3 is equal to 0 or not. So we should be, whenever we are writing next IR representation, we should always be testing whether it satisfies all the conditions or not. So let's see if this satisfies tau2 dot tau3 equal to 0, because I have not used it, right? So 1 minus 2 plus 1. So let's just quickly write down. So 1 minus 2 plus 1 minus 2 plus 2 plus 1 minus 2 plus 1, and we have minus 2, and we have plus 2. So we have 2, 2, 2. So 4 2's are negative and rest are positive. So that means this will be 0. So it does satisfy tau1 dot tau3, which we have used. And we have tested now that tau2 dot tau3 is also equal to 0. Right? So using the same principle, let us keep on writing for tau4. So tau4 will now be, so I'm not doing this calculation again, I'll just read out from my notes, which I've done before. So this is 1 minus 1, 1 minus 1, 1. Okay. Now for tau5, again this will be 1, 1, 1, 1 up to here, and then we have all of them as negatives here. So at each point, I'm not doing it explicitly, but when I'm writing tau5, that means I also tested it for all 4 above. That product of tau5 to tau4 will be equal to 0, tau5 to tau3 equal to 0, tau5 to tau2 equal to 0. So all these are orthogonal to each other. So I should be testing each and every IR representation whether it is following the orthogonality condition or not. Even if one of them is not followed, that means your IR representation is not correct. Okay. So you have to make sure that your IR representation, whatever you are writing, it should follow all the rules of GOT. So, okay, let's write down for tau6. First 3 are positive, then you have negatives up to, and then you have 2 positives. Okay, tau7 will be 1 minus 1, 1, 1, minus 1, minus 1. Yeah, just one mistake can actually screw the whole calculation. And 1. Okay, the last 1D representation is tau8, which is 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1. Okay. And for 2D, again, using the same rules, you can find out the characters for 2D also. So you have 2, 0, minus 2, 0, 0, 2 0 minus 2 0 0. Okay, and for this one 2 0 minus 2 0 0 minus 2 0 2 0 0. So you must also appreciate the fact that all the irreducible representations are uniquely defined by different characters. So none of these two will have same characters at all places, right? So there would be some difference so that they are uniquely defined. Okay, so now that we have written all 10 representations, let us try to find out the Mulliken symbols corresponding to each of these. Okay, so let me just copy this page. Okay, so that I can rub this off. So the Mulliken symbol, let's try to work out the Mulliken symbol. So the 1D representations, as we have learned earlier, so 1D representations have to be either A or B. Now between A and B, it will be A if it is plus or symmetric with respect to principal axis, which is C4 here. Otherwise it will be B, right? So I can say that this will be A, this will be A because it is plus 1 under C4. This 2 will be B. Again I will have 2 A's here and 2 B's here. And then I have two-dimensional representation, which will be E, right? Now doing this, so we have to go one more step forward because it does not differentiate between tau 1 and tau 2, tau 3 and tau 4 and so on, right? So both of them are still A, both of them are still B. So we have to uniquely define the Mulliken symbol for each of this. So now if we go to second part, the second step will be if it is positive under the perpendicular C2 axis or negative or symmetric under the perpendicular C2 axis or negative under the perpendicular C2 axis, right? Okay. And if there is no perpendicular C2 axis, we do have a perpendicular C2 axis. So if there is no perpendicular C2 axis, then we have to go to sigma V. Okay. Also, we can take symmetry under inversion, which will give me a subscript of G or U. So let us write down. So these all four are positive. So I can write G here, G here, G, G, and these are all negative. So negative under I. So this will be U, 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 and this will be G and U. Okay, but it still does not differentiate between AG and AG, AU and AU, BG and BG, BU and BU, and so on, right? Okay. Now, so to differentiate between AG and AG, I can see that this one is having positive character under perpendicular C2. This one is having negative character under perpendicular C2. That means I can say that this one is 1, this one is 2. Similarly, this is positive, this is negative. So I can say 1, 2. Again, it is positive, negative. So I can say 1, 2. Again, this is positive, negative. So this will be 1 and 2, right? So EG and EU are already defined. So there is no need to further give any symbol because this is already uniquely defined, right? Okay. So that gives me the Mulliken symbols for all of this. Now let us also try to work out the basis sets, because it is still not complete character table. So let's try to work out the basis set. So unit vector transformations that we have to take are x, y, z and rx, ry, rz. Okay. So this is a square planar molecule oriented where the molecular plane is lying along xy axis, so z axis is not going to be mixed with xy for sure. Whereas because it has a C4 axis, so x and y are going to be mixed, because we already have seen that there is a 2D representation. That means x and y are going to be mixed. So let us work out the symbol for z first, and then we'll do it for xy. Okay, so let us see which one will give you z. Okay, so z, let's say, so character for tau z, we'll see which one of them is corresponding to z. So under E it will be +1, under C4 it will be +1, under C2 z does not change. Okay, C2 prime z does change to negative, because C2 is the perpendicular C2, right? So plus z goes to minus z. Again C2 double prime plus z goes to minus z. I, it does go to -1. Then we have S4. So S4 again, z goes to -1. Sigma H is the molecular plane. So again, z goes to -1. Right. So we have sigma V, z is positive. Sigma D, z is positive. So this tells me, so if I now match these characters with one of these characters, I see that this matches nicely with A2U, right? So tau z and A2U are same. So that means I can write very safely here that z is forming the basis for A2U. Now similarly, let's do it for RZ. Okay, so tau RZ. So what will be for tau RZ? So tau RZ, E will be 1, C4, principal axis, the character for Z and RZ will remain same. So that will be 1, 1, 1, 1. And then for C2 prime, again it's rotation. So character will be same. So you have -1, -1. So for I, it should be now +1. We have seen the thumb rules. For S4, again, it will be +1, because for Z, it takes the opposite character under S. For sigma H, this is sigma XY. So in that case, Z will go to +1. RZ will go to +1, right? Then you have sigma V. So sigma V is sigma, basically it is containing the Z axis. So that means this will be -1, this will be -1. So this tells me that this is the representation for A2G. Right? So I can say RZ is forming the basis here. Now this is done now for XY and RXR. So XY will clearly be either EG or EU, and similarly RXRY will also be one of those, EG or EU. So let us try to look for which one is forming for. So X and Y together, let's say if we take, so let me again go to next page. So now let's try to write for tau XY. So for E, X remains at X, Y remains at Y. So that means I will get trace as 2. For C4, X goes to Y, Y goes to -X. That means it will be 0, 0. Both of them will be 0, because X is, so suppose if X goes to -X, then for X it will be a -1 trace, and for Y it will be -1. But in this case, X goes to Y because it's a C4, and Y goes to -X. Okay, so both of them will contribute nothing to diagonal, and that will be 0. Now for C2, it will be, let's say if I do a C2 operation here, C2 on XY, X goes to -X, Y goes to -Y, right? So that means both of them are giving -1, -1. So this will be -2 over here. So that still does not differentiate between EG and EU, because so far we have seen 2 0 minus 2, 2 0 minus 2, and then here also it is 2 0 minus 2. Actually, we should directly see for I, because I and sigma h are the only one which are differentiating between the two. So let us see the character under I. So I, if it is applied to xy, what happens? So x goes to minus x, y goes to minus y. So it should be -2, right? So -2 meaning this one. That means I can already see that EU will be the representation based on characters under I, right? So EU will be the representation where xy together will be the basis. Now similarly, if I do it for tau rx ry, the only difference is with I or sigma h, so we can directly see that. So if I do I rx ry, what I get is rx ry. So remember the thumb rules, the rotation vectors do not change their signs under inversion. So that means this will be +2. So rx and ry will form the basis of this. Okay. Now that is done. So that means we have almost completely written this. The only thing which is left is now the binary products, which I leave it for home assignments. So try to work it out yourself, that what will be the basis for different binary products. So you can take example of d orbitals, as we have discussed earlier, and see for yourself that what d orbitals will form basis for which of these representations, and that will go into next column. So over here. Okay, so now we have seen clearly that how to write. So starting from the molecule, how to list down all the symmetry elements, symmetry operations, find out the point group, and then number of classes, order of the group, and so on and so forth. And then using all of this, write down a character table, complete character table from scratch, corresponding Mulligan symbols for each IR representation, find out the unit vector transformation as the basis for different representations, right? Okay, so that finishes great orthogonality theorem discussion with an example now. So in the next class, we'll be looking at cyclic groups and how to write representations for cyclic groups. Thank you very much.